my screen with a proper screen.
I propose hereafter a more intuitive approach for better understanding the fundamental theorem. This theorem states that the distribution of complex amplitude of the electric field in the focal plane of a converging optical system is given by the Fourier transform of the distribution of the complex amplitude in the pupil plane. So here is a complex amplitude in the pupil plane and here in the focal plane. In this video, I have represented a one-dimensional converging optical system, its pupil plane and focal plane. So here is a converging optical system. Here is a pupil plane and also an axis indicating the positive direction of the x-coordinates. And finally, we have the focal plane, also with an axis indicating the positive direction of the p-coordinate. Now, I should indicate three very important points, which are, well, the center of the optical system, the center in the pupil plane, and center in the focal plane. Now, this red segment represents 1/19 of the total length of the pupil plane, which is a line in this case, since we are in the one-dimensional case. And this quantity A of x represents the complex amplitude, of course, in the pupil plane. Here is a very important point, the point H in the focal plane, and where we would like to estimate the amplitude, the complex amplitude. Through this point, we have represented a line which represents a light ray coming from the left, passing through the optical center of the lens, so it's not deviated, and it's intersecting the focal plane at the point H. If you want to know, from the red segment, the light path, followed by a ray which will converge at the point H, well, we just draw here the intersection of that light ray, which is parallel to the previous one, and which, of course, converge at H. A very important line of reference is the one represented in red here. It's perpendicular to all these parallel rays. So you see 90 degrees, which means that they belong to the same wavefront, that all the points are vibrating in phase. In blue, we have represented here the path length difference between the pupil plane and this wavefront, which means that since this point in the pupil plane does not belong to the wavefront, that it will be affected by a phase delay. And this phase delay is represented by this quantity, where P is a coordinate in the focal plane and X in the pupil plane. Now we'll set in motion the red segment in the pupil plane, and we will see how light rays parallel to the two previous ones converge also at point H. And what we see is that indeed the phase delay here is changing depending on the position, depending on the X position in the pupil plane. So we see here, for instance, that just at this particular position, that the phase delay is 0, rather than here it increased negatively, and when it goes down, it increased positively. assuming that this first quantity is a constant, yeah, for instance, equal to 1, well, the contribution of this amplitude to the point H will just be this phase retardation, yeah? And, well, I have represented here in this equation, yeah, the contribution due to the 19 segments, yeah, represented in red. So 1 divided by 19 is the size, yeah, of one of those segments compared to the total length of the pupil. And we see that this expression is just equivalent, yeah, to the integration, the complex amplitude, which in this case, yeah, I just said is a constant, affected, yeah, by the phase retardation, yeah, for each position of the x coordinate.
Okay, so this was the first video, and I will just now move to the second one. So this video is a continuation of the previous one, showing the formation of the image in the focal plane. So I just pressed on start, which should run
19 small segments. And for each of them, yeah, we evaluate the contribution to the complex amplitude of the electromagnetic field, yeah, in the focal plane of the instrument. So we see while we are scanning the pupil plane once, we are moving the H point in the focal plane by 1 unit, yeah, along the P axis. So now P is decreasing. Now here below, what we have represented here are two orthogonal views of the same effect. In fact, AP, which is a complex amplitude in the focal plane, represented horizontally by means of the black dots as a function of the P coordinate in the focal plane. And at the same time, we are representing, yeah, vertically in red color the square of the complex amplitude of the electromagnetic field in the focal plane as a function of the P coordinate, which now is represented horizontally. Yeah. So we see the construction, yeah, of these two curves, yeah, as we are scanning where the focal plane, yeah, as a function of the P position. So here we are almost central. And we see well here that the phase delays, yeah, between the pupil plane, yeah, and the wavefront, yeah, is almost zero everywhere. We get maximum intensity. But as we are scanning farther and farther away, we see that these two planes, the pupil plane, yeah, and the wavefronts are separating, and this induces, yeah, phase shifts, which appear here in this equation. So which is equivalent, yeah, to the Fourier transform, yeah, of the complex amplitude in the pupil plane. So what we obtain in red, yeah, represent in fact, yeah, the point spread function, yeah, due to this particular aperture, which is one-dimensional, yeah, and the other one, yeah, shows a complex amplitude, yeah, which is real in this case, but reach positive and negative values. So this is a sinc function, rather than the red dots represent the square of a sinc function.
Okay, so this is the second video, and maybe it's a good time, yeah, now, just to ask the participants whether there are questions, yeah, whether we'll give another approach, yeah, to the demonstration of the fundamental theorem, yeah. So, are there any questions at this level? Because after we will move to the convolution theorem, yeah, which was already approached, yeah, by Professor Desch, yeah, during his previous lecture, and I shall present some well, kind of experimental approach, yeah. So, is everything clear about the fundamental theorem? So, I see in the chat, yeah. PPT is not visible. Usually, how long is the distance between pupil plane and the lens? Yeah, well, you said the pupil plane, yeah, just at the level, yeah, of the lens, yeah, right, just in front of it, yeah, and the focal plane, yeah, of course, is on the other side, and of course the focal length can be as long as you want, yeah, but pupil plane is really very near, yeah, to the entrance aperture of your instrument, yeah. So this is just to answer the question by, I think, with Zhu, yeah. So maybe I propose now I will share this, my screen, yeah, and go to, yeah.
I just one comment, John.
Yes, please.
Uh, the the second video, the first video is very clear. The second video might give an impression that there is one-to-one correspondence between pupil plane and the focal plane. Points map from one to the other uniquely, and that, you know, as you know, that's not quite true, because every point in the pupil plane contributes to every a given point in the focal plane, and so that that clarification might actually help to people to appreciate that there is no one-to-one correspondence.
Yeah.
Although in geometric optics we tend to draw the rays and follow things through, in physical optics, you know, the situation is slightly different.
Yeah. Well, I had the impression, you know, well, it would be good, yeah, that you visualize once more the video, that every time, yeah, that we were setting the point in the focal plane at a particular P position, yeah.
Function of the P
Yeah,
position.
you see, yeah.
So here
I
we
will
are
just
almost
stop,
central.
just stop the video. So you see, when I have one position here in the P plane, yeah, well, to get, well, the response, which is shown here, you know, we, by means of this red dot, yeah, what we did, yeah, we were scanning, yeah, all these 19 elements, yeah, right? So it's a joint contribution, yeah, from all the points, yeah, to this party for the response function at that particular position. Now, of course, if you would have set, yeah, the point here lower, yeah, in the focal plane, still, yeah, we would get the contribution, yeah, due to all these 19 elements, yeah. So every time we are moving by one step, yeah, the P position in the focal plane, yeah, when we are scanning here 19 elements, and as Professor Desch, yeah, just outlined now, well, there is not one-to-one correspondence, yeah, between the P position and X position, yeah, not at all, yeah, absolutely. I agree with your remark, yeah. So I repeat what I was saying, yeah. So you see here that I'm at a particular position, yeah, in the focal plane. So P equals 0, in fact, here, just at the center. And to get, yeah, the response function of my instrument, which will be a red dot here at P equals 0, yeah, so the maximum intensity, yeah. Well, what I did, yeah, I was scanning the pupil plane, yeah, and taking into account the 19 contributions, yeah, from all these segments, yeah. And of course, now, if I would move, yeah, the P point, yeah, to another position, for instance, here, yeah, well, what I would notice is that still I have to calculate, yeah, the 19 contributions, yeah, to that amplitude here. And this time, of course, I mean, the incoming wavefront, I mean, the phase retardation would not be the same, yeah, as in the first configuration, yeah, but still the 19 segments would contribute, yeah, to the complex amplitude at another position. So there is not a one-to-one correspondence, yeah, between the response function in the focal plane, yeah, and the complex amplitude in the pupil plane, yeah. So I fully agree with that, yeah. But, well, I would advise the participants, yeah, to visualize once or twice, yeah, more, yeah, this video, and then you will find out, yeah, how simple, yeah, is, well, the intuitive comprehension of the fundamental theory. Is it okay?
Yeah, I think.
Yeah, thanks, Sean.
Yeah. I propose to show you a PowerPoint presentation, which is related, yeah, to the convolution theorem. Yeah. You see, this first slide, yeah, shows you a very nice painting, which name, yeah, is Bal du Moulin de la Galette. It was painted, yeah, by a famous impressionist painter whose name is Pierre-Auguste Renoir. And well, if once, yeah, you have the chance to visit Paris, yeah, you may see this original painting, yeah, in the so-called Gare d'Orsay, yeah. So it's a museum in Paris, yeah. Now, yeah, well, what is very nice on this painting, yeah, is that you see, yeah, on at various places, yeah, well, small dots of lights, and you could wonder, yeah, what are these due to? Is it just well, an invention or inspiration from the painter? But I'll explain in a moment, yeah, what they represent, yeah. So, yeah. So on this other view, what you see, it's a table under a tree, and you see, well, dots of lights, yeah, on the table. Then we just make a zoom on this, yeah. So you see, well, some of these dots, yeah, of light look circular or elliptical, yeah, and quite regular. And if you look all around, well, you may see many of these. Here is another view, yeah, it's a photograph, yeah, which was taken at IUCA on the campus. And you may see, yeah, on the floor, very nice, yeah, discs of lights, yeah. And you could wonder, what are these? Well, this is still another view. It's a zoom, yeah, on another part, yeah, of the campus. And you may guess these very nice circular dots of lights. Well, here is a projection, yeah, on the wall of a house, where you may see again, yeah, things looking like, you know, circular discs of light. Here is a zoom, yeah, and everything comes from the principle of the camera obscura, yeah. So the pinhole camera and the sun, yeah. So you may fabricate yourself, yeah, a pinhole camera, yeah, by just taking this frame, yeah. And you see that on the left side of the entrance window, there is a small hole. So it's a pinhole. And on the right side of where the exit aperture, yeah, you see that it should be empty, and you should put there, yeah, some butter paper, so that when you would close, yeah, the whole thing, you will direct it in the direction of the sun, for instance, or of a candle, and you will see, yeah, of course, an inverted image, yeah, either of the sun or of the candle. So here is an example. Here is a pinhole camera. Here is a candle. And here are represented light rays, yeah, coming from different parts of the candle. And of course, we understand that on the butter paper, yeah, what will appear here is an inverted image of the candle. Now, well, I advise you, yeah, if you make one such a, well, box, yeah, well, with a pinhole, that you make it very long, as shown on this photograph, and you direct it to the sun. And, well, you see, there is an angle under which you may see the sun, yeah? And this angular, well, I would call it a solid angle, but along one dimension, yeah, is just a regular angle. The value of that angle, yeah, is 100 over 1 divided by 114, yeah? So, and the units are radian, which means that, yeah, if you'd like to hide the sun, yeah, with your finger, and if the size of your finger is 1 centimeter, you should put your finger at a distance of 114 centimeter, yeah, from your eye to totally hide, obscure the sun. Now you see here on the left side of the image, the projected image of the sun inverted, yeah. And if the length of your box is 114 centimeter, and I would ask you, yeah, what is the diameter of the projected image? Well, it would be exactly 1 centimeter, yeah. because 1 divided by 114, yeah, is in fact the tangent, yeah, of the angle under which, yeah, you see the sun projected on the sky. Now, well, very fortunately, yeah, in the foliage of the trees, there are many holes, yeah, between the leaves, yeah, which means that you see here light rays, yeah, passing through one of such holes, that on the ground you may see a solar disk. Now, this angle is, of course, also 1 divided by 114 radian, which in degrees would be half a degree, or in arc minutes, yeah, about 30 arc minutes. And now, if we would tell you that the diameter of the projected image on the ground is 5 centimeters, well, you could find what is the distance between the projected solar disk and the hole in the tree, yeah? Because you would have just to multiply 5 centimeters by 114, and you would find that, oh, the hole is located at a distance of about 5.7 meters, yeah, from the disk on the ground, yeah. So this is a very nice way to estimate the height of a tree, yeah. Just try to locate, yeah, a solar disk, yeah, projected on the ground, measure the diameter, and just multiply it by 114. Yeah? So 114, yeah, is like a magic number. Now, about formation of solar disk. Yeah? So, well, here is a video. Yeah, here is a video showing in real time, yeah, the projection of the solar disk on the table I showed before. Yeah, and well, these are due to the fact that in the trees, which is just near to it, yeah, there are many holes. And due to the wind, yeah, the leaves, yeah, move and create the holes, and the holes disappear, yeah. So, well, it's very interesting. Now, well, you would like to see, yeah, where the hole is located, yeah, in the tree. Well, you see, you direct your camera, and whenever the light rays would pass through one of those holes, you would see a flash of light, yeah. And this is exactly what is seen on this picture. Now, this is another view, and you see on the upper left, yeah, at Iuka, many projection of solar disks on the vertical wall, yeah. And well, it's a time lapse, yeah. It was edited by Anna, my wife, and you see as time goes, yeah, these solar disks, these shadows are moving, and this is a very interesting question, yeah. What is the trajectory, yeah, followed by those solar disks, yeah, or those shadows, yeah? And well, we may come back, yeah, to this question later, yeah. But now I will just move on, yeah, and go to the next, yeah, slide. Here you see my shadow, yeah, and I'm creating, yeah, solar disk, yeah, by just putting my fingers very close to each other and creating holes between them, yeah. And so you see, if you would multiply, yeah, the diameter of such a disk by 114, yeah, you would know exactly, yeah, what is the distance between my hand and the wall. Now again, the pinhole camera, yeah. So we have seen that if we have one candle on the left, yeah, but located very far away, yeah, from the pinhole box, yeah, therefore you see it moving to the left side, yeah, well, we get an inverted image of the candle, yeah. Now, because the candle is so far away, if you would ask, but through the second hole, yeah, what shall I see? Well, you will see the second image of the candle, of course, yeah, but just translated, yeah, by an interval, well, a distance which is exactly the same as the distance between the two holes, yeah, on the left side of the box, yeah. So it's just a translation effect, yeah. So for the third hole, you see also an image that is being translated, yeah. Okay, if I replace now, yeah, the candle by, well, a heart, yeah, sun-shining heart, yeah, placed very, 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 very far away, yeah. So we know that through the first hole, I see this inverted image, second hole, third hole. Now, if I move the distance between the three holes, of course, yeah, what I shall see, yeah, is the three hearts, yeah, getting closer together, yeah. And well, if it would be a single hole, I would see a perfectly well-defined heart, yeah. But due to the fact that you have a many small holes, yeah, well, the image, yeah, it gets blurred, yeah. And as we shall show in a moment, yeah, this is just a convolution effect, yeah, due to the convolution of the distribution of the holes, yeah, by the shape of the source, yeah, which is a heart in this case, yeah. So this is a summary. I don't know if I can move. No, I cannot move things here. But okay, I have in the upper side, yeah, 3 holes well separated. So I'm getting 3 well separated inverted images. Here they get closer together. So I'm getting well merging, yeah, of 3 arcs. Now it will be even worse, yeah. So the blurring, yeah, is getting worse. And now, well, if you have so many holes, yeah, well, this is what we get, yeah, a totally blurred image, yeah, of the art, yeah. Okay, now this is a small quiz, yeah, that we may, you know, organize online now, yeah. So, well, there will be no evaluation, yeah, following the responses we will receive, but you see, just assume that the source of light is art, sun shining, yeah, set very, very far away. And here I have that many holes, yeah? So this is the entrance and aperture of the pinhole camera, yeah? If I set the screen very close to it, yeah? You agree? I'm getting a blurred image, yeah? Of the arcs, yeah? Which are inverted, yeah? Now, if we go farther away, yeah? Well, of course, I mean, the size of the hearts is larger, yeah? And well, the blurring effect is decreasing, yeah? Now I still set the screen farther away, and this is the image I would see. So you see here, I almost see the true shape of the arcs, yeah? But of course, I mean, there is some dimming. Farther away you go, yeah? The surface brightness, yeah, will decrease. In fact, one could show it very easily, yeah? Is the inverse of the ratio of f to d, where f is the distance, the kind of focal length, yeah? And the d is, in fact, yeah, the size of the hole in the pinhole screen, yeah? So if you go very far away, well, you see that the blurring gets less, but the surface brightness, yeah, gets very, very, very faint, yeah? Now, here is a quiz, yeah? So let's assume that the entrance aperture of your pinhole camera is a heart, yeah, okay? So this is the shape of the pinhole, well, of the hole in the pinhole camera, yeah? Now, let's assume that the source of light, yeah, is the real sun, and the sun goes very far away on the left, yeah? And now, I'm setting the screen very, very close to it, yeah? My question is the following, yeah? What shall I see? Shall I see a sun, yellow sun, or a gray sun? Inverted image or not inverted? Or shall I see a heart, inverted or not inverted? Or would the heart be yellow and inverted or not inverted? So you see the many possibilities, yeah? And just for fun, yeah? Well, I'm asking you, well, you have 30 seconds, yeah? To send your response, yeah? In the dialog box, yeah? Okay? And then we will just see, you know, what are the answers. But later on, yeah, I'll give you the trick, yeah? To always get the good answer, yeah? And of course, yeah, we'll refer to a convolution theorem, yeah, to get the right answer, yeah? So 30 seconds, so I'm just checking. Okay, so I think we only get 6 replies, yeah, which is not a lot, but okay. So the correct answer, yeah, is a yellow heart, not inverted, okay? So we will compare after, yeah, the answer, yeah, to what is known as a yellow heart, which is not inverted. But now, if I set the screen very, very, very far away, yeah, so shall I get the heart, a gray heart, inverted, not inverted, a yellow heart, inverted or not inverted, or a sun, gray, inverted, not inverted, or a sun, yellow, inverted or not inverted. Yeah. So the screen is set very far away. Yeah. Yeah. Now you have 30 seconds. Yeah. To give your answer. Yeah. So just continue. 30 seconds. Okay. Only 7 answers. Yeah. So the correct answer is of course a yellow sun. Yeah. But inverted. Yeah. So of course I'll continue now. Yeah. The keynote presentation, and we'll have a look later, yeah, to the answer which have been proposed, so that it will be fun. Okay, well, the answer would be that, in fact, the intensity you see in the screen, yeah, is just a convolution, yeah, of the heart shape, yeah, by the true solar disk, yeah. But we'll see in a moment why, yeah. So here there is not yet a demonstration, but I'll come to that in a moment, yeah. What I show you here, yeah, is a very nice experiment that you can make at home, yeah, especially if you have a window oriented southward, yeah. So just take a cardboard, yeah, and just drill in the cardboard, yeah, different shapes, yeah, like you see on the left, yeah, are, well, just elliptical shapes, small, medium, larger. Then, well, a star-like shape, then a square, and then a circle, yeah. And below, well, there are only 3 squares, well, with a medium size, big size, and a small size. Yeah. And now what you see, well, this was a master's student, yeah, setting, well, a sheet of paper, which is semi-transparent, yeah, in front of the screen. And you see, if you are very close to it, yeah, you see the real shape, yeah, of the holes, yeah. So you very distinctly, yeah, you see this, yeah. Now, if you set, yeah, the screen a bit farther away, well, the images yeah, get blurred, yeah. And if you set it very far away, what you see is that you get, yeah, for all the hole, each holes, yeah, a nice image of the sun, yeah, inverted image. And even you may see on the upper row that where there is a cloud, yeah, passing in front of the sun, yeah. And well, the most clear image, yeah, is the second upper one, which is the faintest one, yeah, also, because, well, the hole was the smallest for that one, yeah. Now, this is what you see if you set the screen very far away, yeah, so you almost see a perfectly shaped, yeah, solar disk, yeah, from each of the holes, yeah. Here is still another view, yeah. So very nice experiment, yeah, to do for kids and also for ourselves, yeah. Now, well, you can do the same experiment with a mirror, well, taking advantage of the reflection of sunlight. So this is what we did, yeah. So we took some mirrors and put a screen on top of it, yeah. And well, the screen, of course, is perforated, yeah, with the different shapes, yeah. You see star-like, heart, circles, everything, yeah. Okay, and here is what is shown. Yeah, you see on the lower left side, I'm holding one of those mirrors with a mask, yeah, and I just project, yeah, the reflected image, yeah, on the screen, and you see, because I'm so near, that I see from each hole, yeah, a perfect shape of the screen, yeah. Okay. Now, this is a zoom on it, yeah. So you see the right image, yeah, it looks like a butterfly. And now this is when I move away from the screen. Well, I see now the images are blurred, yeah. This is a zoom, and you see the lower right image due to the butterfly, yeah. Well, is really a blurred image, yeah. And we'll understand, yeah, in a moment, yeah, why it is a convolution of the butterfly shape, yeah, with the solar disk, yeah. Now here you see we are in the airport, yeah, with my wife Anna, and now I moved very, very far away from the screen, and here you see on the left side the projected images which are very faint, yeah, but you see 5 almost a clear image of the sun. And of course, I mean, some are very extremely faint, yeah, but it's because of the distance and the decrease, yeah, of the surface brightness, yeah, as you go far away. Okay, now, well, I try to give a brief demonstration, yeah, of what I've shown until now. So in the upper row, what you see on the left is a sun, yeah, very, very far away. And well, in the middle of the row, you see the entrance aperture of the pinhole box, yeah, and you see, well, it's represented by a Dirac function, yeah, in a small hole. And now, well, on the butter paper, yeah, which is on the right side of the box, yeah, what we see, well, it's more or less clear image of the sun, yeah, especially if the hole, yeah, is infinitely small, you will get a perfect image of the sun, yeah. Now, on the second row, what you see is that, well, I just moved, yeah, the location of the hole a bit away from its central position. And what happens? Well, it's just that the image of the sun, yeah, moves in a translation which is exactly the same, yeah, as a hole has been translated, yeah, in the entrance aperture, yeah. So it's a mere translation, yeah. So you see that the recorded, well, surface brightness, yeah, is that of the sun, but displaced, yeah, and therefore it's represented, yeah, at the coordinates p minus r prime and q minus s prime, where r prime and s prime are the coordinates, yeah, of the point where the center of the image is located, yeah, or the center of the hole in the entrance aperture. Now, in the upper row, what you see here, there are two holes, yeah, in my box. So, of course, as expected, yeah, I see two suns, two images of the sun on the right, but which are merely translated, yeah. And now, well, comes, yeah, well, the most complicated, yeah, part of the problem is that, well, I just represent a hole made of a huge number of small holes, and you see it's more or less a rectangular hole, yeah, when you integrate all these small holes, yeah. And what we did on the right side, yeah, well, we just located, yeah, the image of the sun, the real image, at the various points where are located the holes, yeah, the hole centers, yeah. And so what we do, we are just making a summation, yeah, of the translated positions of the sun image. And this is exactly equivalent, yeah, to make a double integration of the shape of the hole represented by the function hole with the variables p prime, q prime, and multiply, yeah, by the real image of the sun, but every time translated, yeah. And we have seen that the translation, yeah, is p minus p prime and q minus q prime. And well, instead of making a summation, we make a double integration on the variable p prime and q prime. And this is exactly a convolution. So you see, the result is a convolution of the shape of the hole function by the sun function, yeah, which is in this case just a perfect circular disk. Yeah. So this is a nice example, yeah, of convolution. So now just remember, when you look on the ground, yeah, at the projection of the solar disks, what you see is just a convolution of the real image of the sun by the shape of the hole in the tree, yeah? So you get information and about the sun and about the hole in the tree. And of course, if the hole in the tree is very small, the image on the ground will be, well, very nice, very well defined, but very faint, yeah? And in fact, yeah, one could show that just look at the, well, end result on the lower right side, yeah, of the slide, yeah? So the convolution product is equal to the function of the hole by that of the sun, convolution product. If you replace, yeah, the hole, yeah, by a Dirac function, yeah, well, the convolution of a Dirac function by the sun will give you the sun. And this is the reason why when the hole, yeah, is a real pinhole, well, the image you see will be the real image of the source of light, which in this case is the sun. Now, if you are very near, yeah, if you set the screen locate the screen very close, yeah, to the hole, yeah, well, you agree that in that case, the size of the sun image will be very small. And you could say, okay, I may replace that one by a Dirac function. And this is the reason why when you convolve the function of the whole with now a Dirac function, you get, of course, as the answer, yeah, that it is a function representing the whole. So when you set the screen very close to the whole, you get, of course, the shape of the whole and not that of the source, yeah, okay? Okay, now, well, in the lecture that you were supposed to visualize, yeah, the lecture 8, yeah, we just considered an aperture, yeah, composed of two apertures, yeah. So, which could be either circular apertures or square apertures or anything you may think of, yeah, yeah. What we had seen during lecture number 7 is that if the circular, well, is the aperture, yeah, is just unique, yeah, or circular, yeah, we know that the response function, or I would say the distribution of the complex amplitude, yeah, in the focal plane, A of PQ, so I'm in the upper row of images now, it's just a Fourier transform, yeah, of the distribution of complex amplitude in the pupil plane, yeah, represented by A of xy, and A of xy usually is equal to 1 if you're inside the aperture, and 0 if you're outside and looking at, it's just like observing, yeah, a point-like source, yeah. Now, on the right side, yeah, we have represented, yeah, the complex amplitude, yeah, in the focal plane, yeah. And, well, we see if the aperture is circular that you get a hairy disk, yeah. Now, if you take two apertures, yeah, well, two circular apertures, like in the lower row of images, yeah, well, we say, okay, we have now to take the Fourier transform, yeah, of this double distribution, yeah, of complex amplitude in the two individual apertures. But this, as a Professor Desch, yeah, showed us, yeah, during his previous lectures, is just a convolution product, yeah, of the distribution of complex amplitude in the original aperture by two Dirac functions. And the two Dirac function indicates where the center of the two apertures are located, yeah. And so you see, yeah, well, this is the first equation in the second row, yeah. The Fourier transform of the convolution product, yeah, of A by the summation of the two Dirac function. Well, we know that the Fourier transform of a convolution product is a simple product of the two Fourier transform, yeah? And therefore now you go to the second equation where we see that simple product, yeah, of the two Fourier transform. And because of the linearity of the Fourier transform, we get that it's the Fourier transform of the original aperture by the summation of the two Fourier transform of the Dirac function. And this we know, yeah? The Fourier transform of a Dirac function is equal to 1, except if it has been translated, yeah? Then it's just represented by the complex exponential which are shown there, yeah? And then we know that the summation of these two complex conjugated, yeah, exponential functions, yeah, just give rise to a cosine, yeah? And this is what you see appearing, the cosine function of pi times b times p, yeah, which is always the same, whatever is the shape of the original aperture, because you see that this is reflected, yeah, in the Fourier transform of A, and we didn't specify, yeah, what was A. It can be square aperture or circular aperture or any kind of aperture, yeah. Now, if we want to take the distribution of the intensity in the focal plane, we take the square, yeah, of that result represented in red, yeah, and this is the last, yeah, equation shown at the bottom of the slide, yeah. We get that it is 4 times the square of the Fourier transform of the original aperture by the square of the cosine, yeah, of pi times b, which is a baseline, the separation between the two apertures, time p, which is a variable, yeah. And if you look, yeah, on the right side, wow, you see that now superimposed on the airy disk, we see, yeah, the fringes, yeah, bright and dark fringes, yeah, yeah. So here we see, yeah, another example, yeah, of a convolution product, yeah, which was already pointed out by Professor Desch in his previous lectures, that these two apertures may be represented as a convolution product of a single aperture by the summation of two Dirac functions located at the position of the centers of the two individual apertures. Okay, now, well, still another convolution product I will show you in the next transparency. And this is also part of lecture number 8. Well, this time, what I represented in the upper row is on the left side a point-like source located well infinitely far away from your optical system, and the optical system is represented by this gray well semi-oval rectangular shape element in the center. So it can be an interferometer. Well, here I just think it is an interferometer. And what we know is that the response function represented by E of the variable P and Q, which is also the intensity observed for the case of a point-like source. Well, this is equal to the square of the module of the complex amplitude distribution in the focal plane. Okay, fine. So this was just a response function of the point spread function of your optical system. Now, what will happen if I'm not locating a source which line of sight is perpendicular to the optical system, but slightly offset in direction. So you see, I have represented it by the delta function, not at the position P prime, Q prime, but P prime minus R prime, Q prime minus S prime, where R prime and S prime designate the location in the sky of the point-like source, slightly offset from the line of sight of reference. Well, I know what I will see in my optical system is a mere translation of that image at position R prime S prime, but with probably an inversion because you know the light ray passing through the center of your optical system will not be deviated. So everything will be turned around. So you see, I have now directed the P and Q axis in opposite directions. Okay, so this is easy. Now, if I'm looking at the 2 point-like sources, as shown in the upper row of the image, what I will see in the focal plane, well, it's just a summation of 2 translated images. Okay. Now we come to the real case. I assume that, well, my source is not represented by a point-like source, but it is an extended source of light. And well, I may decompose it as an infinite number of small point-like sources as represented on the left side of the lower row. Now, what shall I get through my optical system? Well, I know it's just a summation of, well, the alpha k represents the scaling intensity of each point-like sources, because I know that maybe my extended source is not uniformly bright, but I could have variation from one place to the other, So I multiply alpha k, so which is a scaling factor, well, by the image I would get from a point-like source, but slightly translated, And this is exactly a convolution, of what? Just like for the case of the sun, in the pinhole camera, well, here, well, it's a convolution product of the real shape of the source that I would observe if I would have a perfect optical instrument by the response function of the optical system and represented by the function I, P minus P prime, Q minus Q prime. And then, of course, when you multiply by dP prime, dQ prime, well, you multiply by the real size of each source elements, and you perform the double integration to integrate over the whole source extent. So what you get, you see at the end, so lower right equations, yeah, well, it's just a convolution product, yeah, of the real shape of the source, yeah, by the response function of your instrument, yeah. So I will end here. I think this is finished. So I will now stop sharing my screen. And well, I guess there may be some questions now, yeah. So maybe first let's have a look, yeah, because this was funny, at the replies we received. Yeah. So I just look at the series of answers, yeah, for the first one. So the real image would be the sun, sun inverted, dimmer, sun inverted, yellow sun, inverted circle, sun inverted dim. And you remember the first series of questions were in fact yellow heart, yeah, yeah, yeah. Oh, or no, this was the end, yeah. So this was correct, yeah. So I start again, yeah. So this was the first answer, the art, if closed, art, inverted or not. For circles and dimmer, inverted art, shapes and image, non-inverted art, dot inverted. Infra it will say but dimmer. And then, yeah, when we addressed, yeah, the case when the screen was very far away, then the sun, yeah. Sun inverted, of course, yeah. And dimmer and yellow, yeah, of course. These are very good answers, yeah. But you see now that you know that you just have to apply the convolution product, yeah. You say, if I'm very close to the screen, yeah, well, then I know that what behaves like a Dirac function, yeah, is the sun size, yeah, the sun. If I go very far away, well, it is the hole, which is very small, yeah, to the big size of the sun, yeah. So then the hole becomes a Dirac function, yeah. And anytime you convolve a Dirac function with another function, well, the result is, of course, the function itself, yeah. Okay, so now there is some time, yeah, for questions, yeah. So Prakash,
yeah,
do you see any questions?
So that so you guys can unmute yourself and ask a question if you have, or
Prakash, can you hear me?
Type it in the chat. Yes, do you not hear me?
You are muted, probably.
No.
Oh yes, now I can hear you. Yeah.
Okay.
Yeah. So, are there any questions?
Yeah. So I announced that they can unmute themselves and ask.
Yeah, sure.
So is that what you wanted to show, say about the picture in the background as well?
Yeah. Well, the background picture, yeah.
The pictures are too big.
It's just a very nice illustration, you know, of the play between sunlight and the shadows, yeah. And well, we just found it aesthetically, you know, very nice, yeah. And therefore we decided, yeah, to set it, yeah. But here, well, you don't see solar disk, of course, yeah. And well, the light rays you see here, yeah, is a mixture of sunlight rays from Liège, yeah, in at Ayuka in Pune. So I just stopped.
Yeah, it almost looks like you're at Ayuka.
Yes, exactly. Yeah, yeah, correct. Yeah. So
okay, there's a question in the chat box.
In the chat box, yeah. So I just go. Will there be another Hall function if you take two holes one after another of different shapes? Yeah. Well, in that case, yeah. So yeah, the question is, let's assume that in your screen you just drill or perforate, yeah, two holes with different shape. Yeah. Well, then you would just consider that this is a single hole represented by a more complex function, which is a summation, yeah, of these two individual. Yeah. Okay. And well, if they don't superpose over each other, well, then it will be a mere addition. But of course, if they are superimposed, yeah, then you should just take the union of the two, yeah? Yeah.
I think they also mean that what if the light from a source passes through two holes of different functions?
Yes, correct. Yeah.
What I mean is one after the other. It goes through one hole
Oh.
of a different shape and then another.
Oh, I see. Oh.
Then only the common part will go through,
Yeah, well,
depending on how close they are.
yeah, but yeah. Well, what I would advise you to do, yeah, well, I know what would be the answer. Well, the answer could be quite complex, but you could try to simulate, such a situation, especially if you have some sunlight. Yeah, go under a tree. You already have a hole. Then make a second hole in a cardboard. Yeah, and just play around. Yeah, and you will see. Well, I'm very much afraid that the final image will be very dim, but yeah. It's amazing, yeah. Well, it's difficult problem. I mean, you have to set it, yeah, not just to sing, because well, yeah. So I
Yeah,
think
I have
yeah,
a question that I would like to pose to the participants, with your permission.
of course.
Uh, when the example of many holes in the pinhole configuration was shown, where it became a bigger hole, wouldn't we have expected the effective resolution of it associated with it, the diffraction pattern, to be narrower? How come we saw the shadow of the whole, the bigger hole? Why not its diffraction pattern, which would have been narrower?
Yep.
And it's got to do with a very subtle point of where the images get formed, at what distance the images get formed. Where does the translation from geometric optics shadowing translate into physical optics where interference emerges? And that's tied up with the minimum distance you need to travel before the optic system really works as a Fourier transformer.
Yeah, very good question. Yeah.
So the paradox is that when the example of many pinholes close to each other were shown, it was shown as if the image gets blurred by the superposition of contribution from each one of the pinholes. Whereas if that were to be the aperture, I would have naively expected the diffraction pattern of it to be narrower and a much clearer image of the sun.
Yeah, yeah, I absolutely agree. Very good question, because I mean, well, I know the answer, yeah, but if you want me to tell, I will, but it's better.
Asking the participant to think about it, because that will clarify to them the distance at which images are formed and how the minimum distance has to be given before the rays have chance to talk to each other, to interfere.
Yeah.
And that's famously known with the Fraunhofer distance, which is tied up with the size of the aperture and the wavelength.
Yeah, and the size of the source. Well, yeah, I mean, it would be nice, yeah, because I think many people, yeah, like to visualize the things, yeah, that if participants, yeah, could send us a picture illustration, yeah, just well demonstrating. I think with two different representation of the same phenomenon, yeah, one would immediately understand, you know, when the picture I showed, yeah, is correct and when it's not correct, yeah. So the picture I showed, yeah, I will just project it once more. Yeah, this one, yeah. See here, here is a projection of the image, yeah, and it can be true under certain circumstances, but this can be false.
Yeah, can I interrupt? I think this picture is perfect. There is absolutely nothing wrong.
Oh, but yeah,
the one with the pinhole, many pinholes, okay, close to each other, which was shown, for example, the heart was shown to be superposition of the images coming from each one of the pinholes.
Mm-hmm.
That picture, if the aperture amounts to a bigger aperture, one would have expected the diffraction pattern of that to be narrower.
Mm-hmm. Yeah.
And the convolution of the true sky distribution, brightness distribution with the narrow.
Maybe 39, slide 39.
Right.
So slide
Very
30. Yeah.
Yeah, right. I think that's the image. Okay. So there, under what circumstances you see this image as against a bigger aperture corresponding to the combination of the holes, leading to a narrower diffraction pattern, which should convolve with the brightness distribution and give a much finer or better defined image of the sun.
Mm-hmm.
Why does this happen? And what are the assumptions or situations leading to this, where we are practically seeing a slightly smeared geometric shadow of the holes as against the physical optics taking over, where the interference from different parts of the wavefront going through the holes will interfere, which is what was nicely brought out in the last picture that you showed, where the same optic system, okay, what was translated to a different shape of the source itself, right? And you got that is a correct picture. This is where the full telescope optics is made to work.
Yeah. Now I may counter argue, yeah, telling that this image is not correct. You know why?
This is a superposition. Just see, this is not the image you will get.
Yeah.
But this is what you should add together mentally to get the fine picture. Yeah.
Yeah. But now here, well, a more correct picture that I will produce for next lecture, yeah, would be the following one, yeah, is that I should have shown, yeah, a airy disk, yeah, which doesn't move, and when I'm just populating here this image, yeah, with infinitely small elements, yeah, well, it would just act on the interference fringes, you see, yeah, and this would be a more correct representation of what I wanted to convey as a message, yeah, yeah. So here, in fact, well, it means that the source has been resolved by, well, the airy disk, yeah, right? Agree? Here, because, yeah, here it has been resolved by the airy disk, yeah. So, well, it was useless to make use of an interferometer, right? Yeah. So I shall produce another image, yeah, for the next lecture, yeah, in which I will show that, well, the airy disk doesn't move when I consider the different source elements, but the fringes, yeah, are moving, yeah, and this would be then the very correct picture. So, yeah, it's very good, yeah, to be critical, yeah, when you see an image. And for this example, well, I won't give the answer, yeah, what should be done, yeah. So the participants, yeah, yeah. So if you have any good answer, just send it to us, yeah, maybe in the form of a picture or any way you like, you prefer. Yeah. So I stop sharing my screen, yeah. Yeah, so do we have more questions or not?
There's one more in the chat.
In the chat, yeah? So
yeah.
Just go and see. Why do you think it will reduce delay?
No, that's my question back to the original question. So
does
the one just above.
Telescopes along north-south direction reduce delay? Oh, I see, yeah. And here is an answer from Prakash. What do you think? It will reduce delay? You mean due to rotation of Earth? Yeah, yeah. So
just want to know what they mean by the question.
Yeah, yeah. So what do you think? Yeah. So it's Marina Kanti. Yeah. So what do you think? Yeah. Would it help? Yeah, reducing the delay or not? Yeah. So he says yes. Yeah. So you say, yeah, if the baseline is located north-south, yeah, it would reduce the delay. Yeah. Well, of course, I mean, you would need it to be perfectly perpendicular, yeah, to the source, yeah, right? So declination, well, if the declination of the source, yeah, would be exactly equal to the latitude, yeah, of the place where you are, yeah. And then, well, you would just set the delay lines, yeah, pretty well. When you will move left, right, yeah, I guess that, yeah, the delay should remain more constant than if it is oriented east-west, yeah, probably yes, yeah. But, well, about this, well, coverage of the UV plane, yeah, yeah, I'll come up here during the next lecture also with nice simulations, yeah. So we'll try to make use, yeah, of a globe, yeah, and just set on it, yeah, an interferometer and try to rotate, yeah, the globe, yeah, so that everybody will understand, yeah, well, how the UV plane, yeah, is better covered due to rotation of the Earth, yeah, due to change in the linear separation between the individual telescopes, but also orientation, of course, yeah. Yeah, so it's almost 1.5 hours. I'm very sorry, yeah, for the technical problems, yeah, with video presentations, but well, OpenBoard, yeah, is a nice application. But anytime, yeah, you change from one video to a PDF file, yeah, the only way you can use it, yeah, is just to kill this application and start it again, yeah. And well, I read that already in a forum, yeah, that it's not, well, it's not a very handy, yeah, application. Well, if you do very simple things, it works. If not, it doesn't work. So I thought, well, I would maybe try to show you directly, you know, the video with a QuickTime Player, but you've seen it didn't work either, yeah. So yeah, not always easy, yeah, to deal with technical problems, but okay, we are learning, you know. So things will be better during the forthcoming lectures. Let's hope. Yeah. So do you have any more questions? So I hope, yeah, that you will look now, yeah, at the projected images of the sun on the ground, yeah, and just well, figure out, yeah, why it's a convolution product, yeah. So it's very nice, yeah. And now, well, about you know, when I was a student, yeah, well, we had, you know, in the mathematics class, yeah, presentation of what were the conics, yeah. So it means well, study of the ellipse, parabola, hyperbola, etc., etc. And you know, I was really wondering, yeah, well, would it be possible, yeah, to see in nature, yeah, an illustration, yeah, of those curves, yeah, because well, it's not very obvious. Well, of course, the teacher would tell you, well, you know, the orbits of the planet around the sun, yeah, are elliptical, but you never visualize them, yeah, you just see the projection of the path of the planet, yeah, on a small portion of the sky. And now, what I would like, yeah, you to observe, yeah, around 21st of September, yeah, around 21st of September, so the day of the equinox, you could have a look, yeah, at the position of the solar disk on the ground or of the shadow, yeah. And well, if you could take a time lapse, yeah, you'll be surprised to see that the trajectory followed by the shadows or by the solar disk, yeah, is a straight line, yeah, a perfect straight line. And this would be true, yeah, in India, in Belgium, yeah, in Poland, in England, anywhere over the globe, yeah. And well, it's nice to wonder, you know, why it is such, yeah. And well, if you look at a different time, yeah, well, if you look in 3 months later, well, the trajectory probably would be the branch of an hyperbola, yeah. So, which is an intersection of a cone with a plane, yeah. So I already gave part of the answer to understand the phenomenon, yeah. So we may see a very nice illustration, yeah, of the conics, yeah, every day in our daily life, yeah, by observing the trajectory of the shadow of the disk of light, because, well, they could be circles, they could be ellipses, they could be parabola, hyperbola, but it depends on where you are located on the Earth, and also it depends on which period of the time, yeah, yeah. But so, well, it's very nice to meditate, yeah, and to know that, well, we may see in nature very nice illustrations, yeah, of the conic trajectories. So, are there more questions or not? I don't think so, and it's already very late. So next meeting, yeah, is on Wednesday, 14. Yeah, Professor Desch, yeah, will give us his next lecture. So if there are no more questions, am I right, Rakesh? You don't see more questions?
Yeah, I don't see any more.
No, yeah. So we say bye-bye, no? See you on next Wednesday, hopefully, right?
Yeah,
Yes.
bye.
Bye.
Bye,
So
everyone.
bye-bye to everybody, yeah, and have a nice week, yeah.